All right. Hey, everybody. So I sent out an email to y'all about how I'm recording these lessons so that if you miss one or you just can't make it, and yeah, you can check it out on YouTube. And yeah. All right. So, what I've been planning for the beginning of Monday's Zoom sessions is just to go over the homework. So basically, I'll go over the homework questions, the ones I thought were most difficult. If you guys want to go over the answers to other homework questions, that's cool too. Uh, just one thing that this means, though, is that if you can't get the homework done before Monday's sessions, then that's sort of like the absolute deadline, because then I'm going to be posting these answers online, and then it wouldn't really make sense to ask to be grading them. Okay, and then after the homework, today I'm going to cover theorems. So this is the last sort of thing we're going to do on derivations in this course, which is really sad because I love derivations, but not so sad for a lot of other people here who don't love derivations, which I don't understand that at all. Okay. So, theorems, we've covered a little bit of them last week, but more or less they're arguments with only a conclusion and no premises. So they present a special challenge to derivations because you can only really use uh, introduction rules or assumption rules to do them. Oh, hey, Abigail. All right. So yeah, so we'll be doing that, and then on Wednesday we're gonna go on to a new topic, which is making logic into something that's really functional. So we'll be doing circuits and designing circuits, which is something that computer engineers actually use logic for, right? The machines in your phones and uh, TVs and all that use circuits, and circuits are composed of logic gates, which take binary inputs and give a binary output, in the same way that well-formed formulas take binary inputs in terms of truth values and give a binary output. Okay. Uh, so let's get started with these homework questions. So on the screen, I've got number 4 here. So how many did you guys have? Who had difficulty with this question? Nobody? Thomas didn't. Okay, so all right, let's go through this. Am I did I actually write this down right? Yeah, I think so. So last week I was really trying to hammer home this idea that uh, you can use negation introduction to derive a non-negated well-formed formula through this little pattern, right? Where you introduce a negation to get a double negated version of the thing you're trying to get. Uh, and then from there, you can use negation elimination to get the unnegated version. Okay, so this pattern was really important for this question. So if you're using negation introduction, the assumption you're going to have to use is the negated version of the thing you're trying to get. So that would be negation EB. So thinking backwards, that sort of frames this derivation in a way that's really sort of easily accessible from a strategizing standpoint. All right, so we can consider this subderivation basically, derivation with two premises. And it's pretty clear what can happen from here. So we have to get a contradiction. Well, since we have line 1 and 2, that gives us this contradiction in the first premise. Through error elimination. Then negation introduction gives us this guy, and we're done. Yeah, so that was question 4 for the graded homework. And it was, but if you've got this more or less figured out, that sort of pattern there, then that's basically what this question is testing. Okay. This was question 6. So why does this seem so familiar? I think I might have done this question already, or like a version of this for you guys. Okay, so this question, is it question 6? Yes, it is. Okay, so this question, if you're thinking about what is going to be the last rule that gets you this conditional defaulting to conditional introduction, will give us a pretty helpful frame for setting up this derivation. So and then to make it appropriately an appropriate question for the negation introduction chapter, you have to use negation introduction to get this the consequent to that conditional. Okay. So right. So in order to do that, negation introduction, and then line 4, you assume BC. Line 5, now it's sort of, you stop working backwards and you start breaking down these well-formed formula to get at the contradiction somewhere. All right, so the next part is finding out where we're going to get a contradiction. So out of all the atomics, there's only one pair that contradict each other, and that's FA and negation FA. So we can think of that as our goal. In order to get there, you'll have to break down the premises a little bit. So FA, we can get GB and BF from premise 1 using double arrow elimination. And then get GB on its own using conditional elimination or conjunction elimination. Oh. Oh yeah, that would be fine. So Michael asked if I did 5 and 6 within the scope of the first assumption instead, would that be okay? And yes, that is perfectly fine. Okay. And then we got BC and yes, arrow elimination. And finally, we got our contradiction on line 9. So that is FA and not FA. So decently long derivation will take you 11 steps, but not our longest. 8 and 3 lines. So some of you guys will have a shorter section for negation introduction here because in order to introduce that negation, you can actually do most of the work breaking down the premises outside of the BC assumption. So you only really need that assumption in order to derive line 8. Okay. So lastly, we've got this guy, which I think is actually, yeah, it's a little bit tricky, but somewhat easier than the last derivation. So this is question 8. Okay, so it's sort of straightforward in one sense that thinking backwards, there's really only one way we're going to get that conclusion, and that's through negation introduction. So right away, it's like adding a third premise, more tools to use. So we got GB now as an assumption. And in order to discharge that assumption, we need to get a contradiction. So in the premises, we're now thinking about what is the contradiction going to be? And there is one that is really apparent, and that's this negation FA contradiction. Now, all right, so let's just write that down as something we're trying to get. how are we going to get there? Well, we need to get FA by itself and negation FA by itself. Negation FA is sort of easy now that we've made that assumption. So we can just arrow eliminate line 2 and 3, get the negation FA. But getting FA, it's also pretty easy, but it requires a trick that we were talking about last week. So we need to get this well-formed formula. And if you remember, we can actually get that using arrow introduction. So idempotent well-formed formulas like that, what we're doing is we're stipulating that the P and the Q are the same thing, which allows you to derive this. Yes, Reese.
Sorry, it was doing something weird. Could you also do like a reiteration? So like instead of like 6 being the conclusion, line 6 be a reiteration, so that then you have the two lines FA and FA.
Mm-hmm. Yeah, so those are two ways you can do it. I do it this way because it takes up less lines, but if you want to use reiteration, that's also fine. As long as the first line is what you're putting in the antecedent and the last line is what you're putting in the consequent, then that's all that matters. And in that case, the first line is the antecedent and the last line is the consequent. And same for the way I've written it down, because there's only one line. And when you have one line, the first and last line are the same thing. Okay. All right, so now that we have that, we can use arrow elimination to get FA by itself. And we've completed this derivation. Yay. All right. So did you guys have any questions about this derivation? No? Okay. So let's move on to theorems. So a theorem is an argument with no premises but some conclusion. So theorems are, so the P here is going to be a well-formed form, a theorem's a valid argument with no premises and a well-formed form, or no premises and just one well-formed formula as the conclusion. And theorems are, as a well-formed formula, are things that are logically true. So if you remember, if we have a logically true conclusion to an argument. So a well-formed formula that can't possibly be false, then there's no counterexample in the truth table method for figuring out the validity. So any argument where the conclusion's a logically true well-formed formula is a valid argument, which means that if our derivation system and the rules of inference in the derivation system always produce valid arguments when we plug in, when we do the proper steps, meaning if our derivation system's sound, then any well-formed formula that's logically true, we should be able to prove that it's valid using our derivation system. That's exactly what we're going to be doing today. So we can figure out, and we've sort of done this before. So let's take the idempotent well-formed formula, FA, conditional FA. We can even make it more, let's make this more tricky actually. That's really easy. So here's an idempotent well-formed formula also. Right? Because it's in the form P arrow P. So the fact that our language is sound means that we should be able to derive this using rules of inference from nothing. So let's verify first that this is actually logically true. Can you guys think of any possible world where we can change the truth value so that it comes out to be false? Well, one thing you would have to do is make the antecedent true and the consequent false. But that's just not possible because these are the same well-formed formula, right? So it's always going to have the same truth value, P and P. So definitely a logically true well-formed formula. All right, well, let's try and derive this. So since we have the magic of assumption rules, we don't need premises anymore. We can make our own premises. We can work entirely backwards. So in all the theorems you guys are going to be doing, they'll start off with either, it sort of helps because it narrows down, doing theorems narrows down the strategizing and thinking backwards through these things, through derivations. Because there's only a couple rules you guys can use now as the last rule, either arrow introduction or negation introduction. All right, if we're going to use arrow introduction here, the assumption, which is going to be the first line, has to be FA arrow GB. That also has to be the last line. All right, well, there's several ways we can do this. One of them is just to do this reiteration trick, but I don't want to do that. Let's say I want to make this more complicated than it needs to be. I can use arrow introduction to also nest again. So this is what you'll be doing a lot of in doing theorems, is nesting assumptions by working backwards and then working forwards. Okay, we just proved that this is in fact a theorem, right? So if we can take a well-formed formula and show that we can use our derivation system to derive it from nothing, it's doing the exact same thing as doing a truth table for that well-formed formula and showing that it comes up true in all possible models. So that's really interesting, right? So it's showing that our derivation system can do things that do other things, solve other problems for us that we used to use truth tables for. So we don't have to talk about the meaning of these well-formed formulas. We can just do derivations. Uh, Another really interesting part, uh, another interesting aspect of that derivations allow us to do this is that we can find new theorems using our proof system. So we can just start using our rules of our assumption rules and see where we get. And it allows us to explore this possible space of theorems. And that's something you couldn't do with truth tables. Okay, so let's do a more complicated theorem. And I have to make sure I'm not going to come up with one that's the same as your homeworks. So the homeworks, I put the homework up today. So you guys can check that out for the questions. All right. So,
I have a question.
yes.
Sorry. So if you can assume anything and you don't have premises to get to the argument, theoretically, can't you just like get to the argument in every case? Like the conclusion?
Uh, no, so we wouldn't be able to do this for, like, let's say, for most well-formed formulas, like this one. Let's just take a conjunction. All right. So we're going to treat this like a theorem. So how would we try and solve this if we're treating it like a theorem? Well, we'd be looking for assumption rules we can use, right? Since we can't use arrow assumption to get this, we'd have to use negation introduction using our like little trick. Okay, which means we'd have to assume FA negation FA conditional GP. But that sort of doesn't leave us with a lot to operate with as like one assumption. It'd be impossible to finish this derivation. And there's actually, and for most well-formed formulas, it's impossible to treat them like theorems. And that's just because theorems, solving a derivation as if it was a theorem only works if it's a logically true well-formed formula.
And then you have to use assumption rules to prove it, right?
Mm-hmm.
Okay, that's right. Okay, thank you.
Okay. So let's see, something that's logically true. Okay. All right. So what I've done here is just taken something that's logically false and put a negation around it. And that's logically true. All right. So how would we prove that this is a theorem? All right. The main connective is a negation. So that gives us our first big clue on how to try and solve this. I might need a lot of space here. Yeah. Okay. So that gives us the following well-formed formula. Then what do we do from here? So we need to find a contradiction. And there's sort of a contradiction available in the premises here. So negation FA and GB and FA and GB are, you know, the opposite of each other. So I think that's the contradiction we're likely to get here. I just have to think through how we're going to get it. So let me make sure this is actually solvable. Yeah. Okay, we'll have to use negation, introduction. This is going to be sort of weird. So here's the contradiction that I'm supposing we're going to get. All right, how do we get there? Well, we need negation, we need FA and GB at some point, and negation FA and GB at some point. Okay, so since all we have is that first assumption to use, one thing we can do is try another negation introduction. So one of these things that we need, we can introduce using negation introduction. And through that, we'll get negation FA and GB. Oops. Important to note at this point that this doesn't count as what we're trying to get. So it's always tempting to try and pull those things out of the to take them out of the assumption lines that they occur in and to try and use them to solve the derivations early, but we can't do that. It's against the rules. Uh, it makes doing derivations way too easy, and that would be against the fun of doing these things. Okay, so once we have lines 2 and 3, we've got our contradiction. So we get line 3 through double arrow elimination on line 1 and 2. And then we can use the same trick again to get, we can't use reiterate at this point because it's outside of the scope of lines 2 to 4, but we can get this using double arrow elimination. So now we've got our contradiction, conjunction introduction, and cite everything for negation introduction. So 1, 2, 7. Okay. So any questions about what we just did? So this is a pretty classic difficulty theorem proof. And usually theorems will have multiple assumptions being made within them. So it's like an especially important type of derivation to be comfortable navigating like the scope lines to make sure that you're not breaking the rules and doing a theorem. So for example, on lines 2 and 3, we've got sort of what we needed in order to finish this first scope line if we weren't paying attention to the fact that line 2 is an assumption to a new assumption rule. And that makes it inaccessible to this first scope line. Okay, so that's going to be the biggest challenge, I think, for doing theorems, or at least I've found, is that navigating the different scope lines and making sure that you're not, breaking that accessibility rule. All right, yeah, so let's do one more theorem. And I'm going to take, they're sort of hard to think of. So I'm going to take one from the homework. Wow, yeah, this one looks really difficult. This should be fun. Yeah, I might not actually be able to do this, but I should be able to. Let's see if I can. All right. So here we've got a theorem. Let's just trust that. So whenever you're doing these theorems, the first thing I'm thinking of, at least, is am I going to use negation introduction or error introduction? And I think I've said this before, but you should always prefer error introduction to negation introduction. It's just a lot less messy to work with. Okay, so we assume JB in that case, and we're trying to get to this and now how do we get from JB to HA disjunct negation HA? So this is going to be a time when we use our superpower of negation introduction to help save us. So one thing to keep in mind here is that disjunct introduction, if we get either HA by itself or negation HA by itself, we've got, the full disjunct if we want to. So let's just say we're going to try and get negation HA by itself. I actually don't think this is going to be the strategy we want to try. Because now we have to get a contradiction. Maybe. I think I know what we have to do. Okay. So that's not the way. I don't think so, because it doesn't give us enough resources to use, So let's try and get this. Okay, now we're trying to get a contradiction. And I think that now it might actually be, yeah, okay, I see what we have to do. Now we can do what we were trying to do before. So, yeah, this is a fun one. Okay. So I think the contradiction we're actually going to end up getting here is negation HA. And the way we're going to get that is using negation introduction again. Let's give myself space to do some of these rules. Okay, and then we assume HA. And so with these three assumptions, I think we can actually get somewhere. Because with HA, we can just create the other side of the contradiction for using negation introduction. By using disjunct introduction. And then we get the contradiction. We need to close off this. So it's pretty fundamental to theorems that a lot of what you're trying to find overall is just some contradiction. Because if you think of proving a theorem, what you're really trying to show is that assuming the opposite of the theorem is going to get you a contradiction. So negation introduction or proof by contradiction is pretty fundamental to theorem proving. This is line 7 here. So since line 4 is outside of the scope of this assumption, we have to do that disjunct introduction again. Seven and 2. Okay, yeah, this was a fun derivation. Pretty challenging. Maybe more challenging than I would put. This would be like a bonus question, I think, just because it's sort of tricky. So line 2 to 8. But I'm glad I chose this to do for you guys because it shows this dilemma, right? I was uncertain at line 10 how we were going to get that disjunct. It was either we could go trying to derive one side of the disjunction, one component, and then introducing that component, the other component, using disjunct introduction. But it turned out that negation introduction was actually the way to go. And one thing that sort of made it apparent that that was the way to go was that just introducing one of the components didn't give us enough to work with if we made an assumption based off of that. Line 9 and then line 11. That is 1, 2, 10. All right. So any questions about this derivation? If not, that's it for this Zoom session. I'll see you guys on Wednesday.